Okay, so I'll have a recap of lecture 8.1. In lecture 8.1, we had discussed about critical clearing angle and critical clearing time, how we will derive critical clearing angle and critical clearing time when the fault is near to the sending end bus. This is the sending end bus, this is the receiving end bus. If the fault is near to the sending end bus, what will you do? So from this we have drawn the power angle plot, which is electrical power versus power angle. Then using equilibrium criteria, we have found the expressions for finding the clearing angle. Initially we have found the expression for finding clearing angle. Then we derived the equation for clearing time Tc, then critical clearing time Tcr and critical clearing angle del Cr. Okay, just we made this del 1 as del m. That means I'll show you here. Here, this del 1. This del 1 is the extent of swing that the rotor has. So if the extent of swing is such that it reaches here, this point, where PE equals P max. If the swing goes beyond this point, then again PE will be less than PM or PM will be greater than PE. So in that case, rotor will again further accelerate and A2 will be larger than A1. In that case, it may not come back to synchronism. So the system may go unstable. So basically this point is your del M. So corresponding to del M, if your clearing angle is somewhere to the right side of del C, the maximum extent to which the clearing angle can happen so that A1 equals A2. That condition we have taken and we have found the del CR at this point, and the corresponding time is TCR. Now in the second case, that is what will be discussed now. There is a small change in the figure. I tell you, yes, here. Now we are taking the fault away from the sending end. That is, bus 1 is the sending end bus. Now if F is away from the sending end, somewhere at the middle or at the 3/4 length of this particular line, somewhere. Okay, then what will happen? So let's see now. The initial steady state, this is the power angle curve corresponding to that particular system. So you can see curve A, which is the highest curve. Curve A is the electrical power curve before fault. So before fault, in the sense, initially the system is working at power angle del naught, and what happens is at point A, at state point A, we will have a fault at line 2, away from the bus 1. Okay, so in that case, the state point drops to point B, because your equivalent transfer reactance of these two lines is going to, what will happen? See, this will look like some delta network, because here if this is grounded and this is grounded here, then it will look like some, so this part will look like this. And if you take the equivalent circuit, we'll see this in the next lecture in detail, because we have to use numbers to justify this. But just understand that the equivalent reactance, transfer reactance increases. So when equivalent transfer reactance increases, what happens to the power transfer capability? We have V1, V2 by X sin del, right? Where V1 is the voltage of the sending end and V2 is the voltage of the receiving end, and X is the transfer reactance. So if X increases, basically electrical power decreases. That is why from A, the state point dropped to B. So this is the curve now. So now the electrical power is governed by curve B, which is electrical power during fault. So now what about the relative difference between PM and PE? Now PE is less than PM. So now the rotor starts accelerating through this curve until point C, where the fault is going to be cleared. So at point C, when the fault is cleared, what happens is the second line is completely taken out. This is completely taken out. So only the first line would be there. So again, what happens is reactance will decrease, but not to the level of pre-fault condition, as in the pre-fault condition, but it decreases. So again, transfer capability is going to increase. So from C, it picks up to E. The state point picks up to E, and at E you can see that again PE is greater than PM. PM is PI here. Okay, the input power PI. In some textbooks it is given as PM, mechanical power PM. So again PE is more than PM. That means it's deceleration. It corresponds to deceleration. So the rotor decelerates till point F, which is the extent of swing for the rotor. So at F, you see that this is del M. Okay, let this power angle be the corresponding angle be del M. So in the section EF it decelerates, and in the section BC it accelerates. Now, how will you apply equal area criteria here? Because in this section, in the accelerating section, we have area as PM minus PE, where PE is governed by curve B and PM is a constant, which is the horizontal line here. So PM minus PE means this is the area, right? Now in the deceleration area, we have PE minus PM because PM is less than PE, and PE is governed by the curve. Which curve governs PE here? In the post-fault condition, curve C. Okay, curve C governs PE in the post-fault condition. So this is that area. So we'll apply equal area criteria and find whether what could be the critical clearing angle. Now, what is critical clearing angle in this case? Let's see another figure here. Suppose your fault is cleared only at this point, del CR. And if you have the decelerating area till F, where F is a point on the mechanical input line, okay, then beyond this, if the swing goes, if the swing extends beyond this, then what happens is again PE will be less than PM, and the rotor may accelerate and it may go out of synchronism. It may not come back to synchronism again. Okay, here accelerating area is greater than decelerating area. So acceleration is more, basically the energy gained by the rotor is more than the energy released by the rotor. So it will accelerate again and it will go out of synchronism. So this is del max basically, because this is the extent to which the rotor can have swing. So if you delay your clearing, then it can go till this point. If your clearing is delayed such that del goes beyond this del max, then it will not come back to synchronism. So there we have to find the critical clearing angle here, and the corresponding time you have to take, evaluate as TCR, which is the critical clearing time. Now let's apply the equal area criteria. So we have three curves A, B, and C, where A is the pre-fault curve, B is the during fault curve, and C is the post-fault curve. We know that it's basically a half sine wave. So electrical power output equals P max sine del, and we are going to take B as a scaled down version of curve A, because we know that the amplitude is less, but still the pattern remains the same. It is again the sine curve, right? The PE corresponding to B, the curve B. So we are multiplying this with K1. K1 into A, curve A, will give you K1 into P max sine del. Similarly, we give for C also some other scalar we are multiplying to curve A. So K2 into P max sine del. Now what about the relative difference between K2 and K1? What about the inequality of K2 and K1? K1 is less than K2. That means we know that curve B is the during fault condition. Curve for during fault condition. So that is the smallest one, right? So K1 is less than K2 we are taking. Okay, until this point, is it clear? Everybody?
Yes, sir.
Yeah. Now, let's apply the equal area criteria. So we have PI equals PM, or P Pi equals Pe. Pi is P input, which is mechanical power itself. So in the initial steady state operating point, we have mechanical power equals electrical power. So Pi equals P max sine del naught, because the initial steady state power angle is del naught. So this is P max sine del naught. Now del max is equal to del M. Okay, del max is equal to del M here. Now del max, this one, because we want to find the critical clearing angle. So we take the swing up to this point F. Okay, now the area, the accelerating area will take as integral del naught to del CR here. Integral del naught to del CR, this whole area we have to take, because PM minus PE we are taking, PM is greater than PE, and this is the section in which the rotor accelerates. So to find the accelerating area from del naught to del CR, we are going to take integral del naught to del CR Pi minus B. Right, B is the curve. B we have already evaluated. B is K1 into P max sine del. Right. Now Pi minus B d del equals area 2. Area 2 is decelerating area. Decelerating area starts from del CR and it ends at del max. So the limit is from del CR to del max, and here PE is greater than PM or PI. Okay, so for this area we are taking C minus PI, that is curve C. Curve C corresponds to K2 into P max sine del, C minus PI d del, del CR to del max. So these are the two limits. Now we are going to substitute for B and C. B is K1 P max sine del. So we are substituting this integral del naught to del CR Pi minus K1 P max sine del d del equals integral del CR to del max. For C we are substituting K2 P max sine del minus Pi d del. Okay, now substituting Pi equal to P max sine del. Here Pi is not P max sine del, it's P max sine del naught. Okay, this is the initial operating point Pi, because here you can see initially we have Pi equal PM equals Pe naught, which corresponds to del naught. So which is equal to P max sine del naught. Okay, so we are going to substitute that. When we substitute that and we simplify, that means we have already substituted for B and C with respect to K1 and K2. Now for Pi we are going to substitute P max sine del naught. If you do that and if you simplify, you get cos del CR equals 1 by K2 minus K1 into del max minus del naught into sine del naught plus K2 cos del max minus K1 cos del naught, which means if we know the initial operating point del naught and if we know del max, then you can find the critical clearing angle. So in the coming problems, in the numerical examples, which I'm going to post tomorrow, we will see these equations. Okay, this is just a concept.